All right, so we continue with Kawabuchi Shinya, who will tell us about a q-analogue of perfect Matroid designs. Please.
Thank you for introducing me. Hello everyone, my name is Shinya Kawabuchi. I am in a second year of master programs at Kumamoto University in Japan. In this talk, I will discussing some properties of Q-perfect material designs. Perfect material designs are materials whose all flats of the same rank have the same cardinality. One of the most interesting properties of perfect material design is their relationship to the combinatorial structure called a design. Combinatorial designs are characterized by their balance property, and I introduced their detailed definition in former part of this talk. As a relation between combinatorial design and perfect material design, it is known that flat circuit bases form combinatorial designs. In recent years, q-analogue of Matroids have become a major research focus because of their application to rank metric codes. Subspace designs are also q-analogue of combinatorial design, and there are wide applications to network coding theory in communication engineering. In 2022, Imia Ban and her collaborator established the q-analogue of perfect material designs. They found that the construction method of q-perfect material designs using a q-analogue of Steiner systems. However, the works focus mainly on q-Steiner system. So the general properties of q-perfect material designs remain largely unexplored. Let's begin with the fundamental definition of Matroids designs and perfect material designs. I will define Matroids based on the axiom of flats. Let E be a finite ground state E, and let the flat F be a family of subsets of E, satisfying following condition F1 to F3. F1 states that the ground set E is flat. The F2 states that the intersection of flats is also a flat. The F3 states that the augmentation conditions for flats. Then the pair E and F is a Matroid. For example, let E be 1, 2, 3, 4, 5, 6, 7, 8 set, and flats F are these 16 subsets of E. Then the pair E and F is a Matroid. Let's check the actions. The ground set E is in flat, and F2, the intersection of flat 1, 2, 3 and the flat 2, 5, 7 is a single element set 2, and the set E is also a flat. If we choose a flat 4 and an element 6 in E, there uniquely exists a flat 2, 4, 6 covering flats 4 and including an element 6. So the pair E and F is a Matroid, and this Matroid is called a Fanon Matroid. Due to the flat action, we can define rank of flats. The rank of flats is the length of maximal chain from flat H, where H is intersection of all flats. In Fanon Matroids, the single element set 1 is a rank 1 flat. The ground set 1, 2, 3, 4, 5, 6, 7 is a rank 3 flat. Next, we define combinatorial designs. Designs are defined by a point set E and a family B over k element subsets of E, called blocks. The pair E and B is T designs with parameter nk lambda, if and only if every T element subset of E is contained in exactly lambda blocks of B. For example, if we take two element subsets to 4, there is exactly one block 2, 4, 6 in block. Similarly, if we take two element subsets 3, 5, there also is exactly one block 3, 4, 5 in blocks. So the rank 2 flats of fan Matroids are to design with parameter 731. If the lambda is equal to 1, we call the design a Steiner system. So the rank 2 flat of fan Matroid is a Steiner system with parameter 237. Perfect Matroid designs are Matroids whose all flats of the same rank have the same cardinality. For example, a fan Matroid is perfect Matroid design because all rank 0 flats have 0 element and all rank 1 flats have 1 element and all rank 2 flats has 3 element and all rank 3 flats have 7 element. We denote the size of flats by alpha sequence. For instance, a Phanomatroid has an alpha sequence 0, 1, 3, 7. The only known classes of perfect Matroid designs are limited to uniform Matroids and subspace of affine space or projective space or Steiner system and affine triple system. And these perfect Matroid design is determined in this way. One of the interesting facts about perfect Matroid design is that the number of rank I flat is depend only on their alpha sequence. The number of J flats in the interval between a rank I flat and a rank K flat is depend only on the alpha sequence. The number of J flats in the interval between a rank So we can define flat enumerating function called T function of a perfect Matroid design. For example, TM023 represents the number of rank 2 flats of fan Matroid, and the function returns 7, and there are exactly 1, 2, 3, 4, 5, 6, 7 of rank 2 flats. Similarly, TM123 represents the number of rank 2 flats between rank 1 single element set and the ground set and returns 3. And there are exactly 1, 2, 3 of rank 2 flats between this rank 1 flats and the ground set. Next, we define q-analogue of Matroid designs and q-perfect Matroid designs. The concept of the q-analogue is exploring what happens when we generalize certain properties from a finite set to a finite dimensional vector space. For example, elements in the sets are regarded as one-dimensional subspaces of the vector space. Subspaces are regarded as subspaces. The size of sets corresponds to the dimension of the vector space. The union of two sets is regarded as the subspaces of two vector spaces. The intersections are regarded as the intersection of vector spaces. For instance, we can enumerate the number of k-dimensional subspaces of a vector space by the recursive formula like this. This is regarded as a q-analogue of the combinatorial recursive formula. By taking q-analogue of traditional Matroids, we can define q-Matroids. A q-Matroid is a pair of vector space E and a family F of subspaces of E following these conditions. The ground set E is flat, and the intersection of two flats is also a flat. And the augmentation condition is held in q-analog way. Then we regard an element of E is regarded as one-dimensional subspaces of E. Similarly, we can also define subspace design as q-analog of T designs. In subspace design, for all T-dimensional subspace, there are precisely lambda of blocks which contain the T-dimensional space. If the lambda value is 1, it is called Q-Steiner system with parameter Tk and Q. Now we've arrived at the main topic, so we can define the q-analog of perfect Matroid designs. Q-perfect Matroid designs are q-Matroids whose flats of the same rank have the same dimension. This definition is just a q-analogue of perfect Matroid designs. The alpha sequence of a q-perfect Matroid design represents the dimension of the flats. We can easily construct q-perfect Matroid designs by taking intersections of all subspaces of k-dimensional subspaces. A non-trivial case of q-perfect Matroid design can be constructed by taking intersections of blocks of a q-Steiner system. This fact is found by Emir Bern and her collaborators. Next, we show some results about q-perfect Matroid designs. As a fundamental property of q-perfect Matroid designs, we found the enumeration function of flats. The number of j flats between I flat and k flat is equal to this function. So we can define q-analog of t function for q-perfect Matroid designs. By using this fact, we can easily show that the equivalence of q-Steiner system and q-perfect Matroid designs. In other words, a perfect Matroid design is induced by q-Steiner system with parameter tk and q if and only if a q-perfect Matroid design has the alpha sequence 0, 1 ellipsis t minus 1 kn. To give a proof for the equivalence between q-perfect Matroid designs and q-Steiner system, this theorem and the corollary is useful. This shows that the flats of q-perfect Matroid design form a t designs. If we substitute k to t, we can get q-Steiner system in the family of all rank t, and this corollary indicates that q-perfect Matroid design with parameter 0, 1 ellipsis t minus 1 kn induce q-Steiner system with parameter tkn. By using t function and the last corollary, we can give a proof for the equivalence. As traditional Matroids, we can define the Möbius function and the characteristic polynomial of Q-Matroid. The Möbius function is defined on the flats. The characteristic polynomial is defined by the value of the Möbius function. There is weight enumerator of Q-Matroid, which is defined by the characteristic polynomials of contractions of Q-Matroid. Contracting of Q-Matroid can be determined by the quotient space, but due to time constraints, we will omit the detail. One of the fundamental problems in Matroid theory is determined whether a given Matroid can be represented by a specific matrix. The representation problem for Q-Matroids is representing a Q-Matroid by a Gaussian cause. Gaussian cores are linear cores on a field F of order m's power of q. In Gaussian cores, the weight of code words and distance of two code words are defined by the rank of matrix representations of the code words. The weight enumerator of the Gaussian code is polynomial whose coefficients corresponds to the number of code words of its rank weight. It is known that the weight enumerator of Q-Matroids is equal to weight enumerator of their Gaussian code representation. However, we note that we can define weight enumerator of Q-Matroid. Nevertheless, the Q-Matroid is representable or not. For Q-perfect Matroid designs, the Möbius function, the characteristic polynomial, and the weight enumerator are determined only by the alpha sequence. By using t function of q-perfect Matroid design, we can substitute sigma on flat to sigma on the rank. So we can calculate the weight enumerator of q-perfect Matroid designs recursively by their alpha sequence and the order of the field. As we showed, q-Steiner system is equal to certain q-perfect Matroid design. So we might be able to explore the existence of the q-analog of Fano planes, known as a q-Fano plane. A q-Fano plane is a putative q-Steiner system with parameters 2, 3, 7, 7, and its existence is still an open question. However, Q-final plane are equivalent to QPMDs with alpha sequence 0, 1, 3, 7. So we can calculate the weight enumerator of their putative capital code representation. By using free software SageMath, the weight enumerator of Q-final plane on a field of order is this function. The weight enumerator of Q-final plane on the field F of order 2 indicates that it cannot be represented over the field of order m's power of 2 for m is 1, 2, 3, 4, 5, 6. If we substitute variables to t to certain parameters, the number of code words with weight of 6 or weight of 7 become negative. However, we must notice that this fact doesn't state that Q-final plane is representable on field of order 7th power of 2. In the end, I introduced some topics. The non-trivial Q-Steiner system is only with parameter 2, 3, 13, 2. For another example of QPMD, we need another Q-Steiner system. So it is important to determine the existence of Q-final plane. It is known that some traditional binary codes and Steiner systems are equivalent. For example, extended Golay codes and Steiner system with parameter 5, 8, 24 is equivalent. So I want to know whether the Gabbian code with this weight enumerator induces a Q-final plane or not. Secondly, there are some PMDs not induced by Steiner system, but non-trivial constructions of Q-perfect Matroid design without Q-Steiner systems have not been known yet. Quantum Matroids seem to have similar property of Q-perfect Matroid designs. So I want to study the relation between Q-perfect Matroid designs and quantum Matroids. Thank you for your kind attention.
We have lots of time for questions. Now it's on. Oh, too close. All right, well, okay.
It seems like when you take a limit of q goes to 1, you recover the original formula on number of flats.
Yes.
Yes,
For
so I
example.
wonder whether one can like argue in a certain way that this implies the original formula.
Original formula of this is
Like
yeah.
you take a limit q goes to 1, then you recover, but
Yeah.
is there like some justification?
We can show this, but I didn't. Yes, the function Tm q alpha k power of q minus q alpha I plus L power of q over this, and we take q to 1, we can get alpha k minus alpha I plus L over alpha j minus alpha I plus L. We can get, but proof is not. I am prepared. I'm sorry.
Any other questions? All right, let's thank Shinya again.